No.
Hello.
Don't know if you might be interested.
That's a look.
Yeah.
I've been studying this sheet a long time, right?
Oh, that's right.
Even though I know every day every time you hear, you just.
Funny, it's looped back around to being correct. But I was incorrectly put in here as a computer science PhD.
Oh,
And now I'm switching next semester, so it's
okay, yeah. I just copied from the roster. So.
Hello. How's it going?
Pretty well. What about you? Average?
Yeah.
Less than average?
Yeah. Take the average up like both ups and downs. Yeah.
luckily as time goes to infinity, I'm dead, so it works out. Don't have to really worry too much.
Yeah.
It's I guess we're gonna sign it today. Fabulous.
Yeah, I know why. Jacob. Did you see anything I want to ask?
Yeah.
Did
Did you see we're supposed to have another dinner tomorrow?
Oh, you mean on the syllabus?
No, on the blackboard.
You posted another homework? That's nice.
We never gave us one.
Oh,
but
okay.
it's due.
Oh, yeah,
Little by little.
his dates have been off on that for a
And
minute
then
now.
we can just talk.
Communicate
Yeah.
I think he's just kind of, I don't know, maybe he's adjusting them.
So you
because
can understand
I still gotta get
what we are talking.
Yeah. At
People
this
talk
point,
about
just
how
what you
useful
have.
languages. It's like, I don't care how
For-
useful it is. I just want to talk about
Four,
people.
honestly, I
Yeah,
can't
that's
get started on four.
Yeah.
I was looking at it just a little bit ago, and I think.
It's like, oh well, I could learn Spanish, but I don't think I'm Spanish. I talk Spanish too, so
Because
there's
he
no
said you used
motivation.
the partition function.
There's motivation to learn football. So
Then he tells us to find entropy.
You
Didn't
don't
there.
understand.
Yeah, I would didn't win.
It's probably over 50 people already. Did y'all RSVP for the graduate student Halloween party?
No.
I sent the
Is it Discord?
link in Discord, I believe. But yeah, it's starting to get filled up. So if
Oh,
you wanna,
How many,
if you wanna
how many spots are
coupon
open?
How many
There's
spots? Yeah.
like 100
Okay.
Like total or remaining?
total.
You said 100
It's a
remaining.
week.
I'm like, 4,000 people are going? Oh my gosh.
Impressive.
I'll do that right now.
Good marketing.
Stanford said you took out the J's.
Yeah, take out the J's.
But when I take out the J's, I get errors and it won't run.
Let me see what you got after this, Bobby.
Well, I took out the J's first and all I got was errors.
You gotta take out the J and then adjust the array. That was a bar.
Just the array.
Yeah. I can show you what I did.
Because if I can get that running and it looks reasonable, the rest is pretty easy. It's,
Yeah, Dr. Smidigi had given me a suggestion which made it look a lot neater.
I wish he would comment his code. Make this a lot easier.
So I tried sending resend that list as a decoration
Oh.
because she couldn't get access to the list that I created. So I did the same thing. That way she can try to order tomorrow. We'll be here tomorrow.
I think it's Amazon.
Fill that out on Discord.
I would hope that U of L has Prime. Prime student.
You did too.
That's surprising.
It's everything.
I gotta do something different for the gift card. We can still do gift card, but it can't be an actual.
Interesting.
We would not read, yeah, let's start it. Just remind you, we last time discussed the potential barrier. Like this, we have potential barrier for given the barrier is V naught. And depending on the initial energy, there is higher than V naught, which is lower than V naught, or there is potential well. So let's just remind you one case by case, right? In case if energy is larger than the V naught, we know classically it's 100% transmit. But what we found is there's a resonance phenomenon for the transmission. In this case, quantum mechanically, the transition coefficient is here, right? Transmission coefficient here we have introduced lambda and epsilon. Here the epsilon, because its energy always higher than V naught, so that starts from 1, not 0. That is some mistake in figure 4.4. I just tried to. And here, this one I don't have space, but I will discuss here. So finite one value here depends on the height of this. So it's higher or lower. You will see this value will either go to small transition or even higher. So that is for this case. And the resonance is follow this. For each case, if we have the n, 1, 2, all this quantum number. So this phenomenon also found in this case for the potential wave. Potential wave, the potential, this is negative. So if energy is always higher than 0, so that means higher than in this above this wave, right? Then what we found is the transmission coefficient almost the same as this one, but in this case epsilon plus 1. This is epsilon minus 1. Then because here we introduce epsilon is the ratio of energy to the absolute value V naught. This V naught in this case is the absolute value. Then energy from 0 to all particles, so epsilon can start from 0, 1 to all the others. Here it starts from 1, right? So that is one thing is different. Then but the similarity is here. We have same, I'm going to say the same of the resonance phenomena things we found at some particular energy, we have 100% can transmit. So some of the energy is some of the interference by this wheel, but in some particular energy will 100% go over. So that is this case. And energies follow here, we have a minus. Here require this energy to be positive, so that means you have select n such that this one is larger than this one. Right? That is the case. Then we go to the third case. So come back to here, the potential barrier. If the energy, I just put it here. Again. So in case energy is here. For this case, then classically it will not go through, it will, at this age, it will come from the left-hand side, it will 100% reflect, right? No any possibility the particle pass through this barrier. But what we found quantum mechanics, we still have a transition coefficient follow this formula here. This is a hyperbolic sign. And here is 1 minus epsilon. So here, since this ratio, energy is lower than the V naught, right? So that's the always smaller than 1. Then we can also let's discuss this case. Continue discuss with this one, and then they are going to finish. So when this epsilon is much smaller than 1, that it means this V naught is much higher than the initial energy. So higher, classically, there is no transmission, but how high in quantum mechanics to affect this possibility to transmit the barrier we call the tunneling. This tunneling effect, right? So let's consider in this case. In this case, if this is larger, then this epsilon is smaller than 1, so we can use this one as the hyperbolic sign x actually is approximately equal to x lambda 1 minus epsilon. Then we're going to substitute into here. You will find this transmission coefficient is approximately equal to 4 epsilon 1 minus this term go to the numerator, and the denominator is this is science, this one, but hyperbolic sign is exponential. Sorry, it's exponential lambda. It's a positive term, right? By factor 2, because if a hyperbolic sign is this term minus this minus term, right? Then when this is a larger lambda is larger than that term, ignore. So here we have this one, exponential lambda. So that gave us, if you just substitute this, substitute this lambda and epsilon into this formula, you will see which control they give us. Number is depend on energy and of course this potential barrier, how high it is. That is not there, right? So that means even the energy barrier is very high, we have a instant energy is not high enough compared with this barrier, we still can transmit. That is the famous tunneling effect. Okay, this is first. Second, if the epsilon is close to 1, that is energy just.
Is this the sign hyperbolic?
Yeah, this is a sign hyperbolic. Yeah, this one. But these two are sign.
Okay.
Yeah, that's the, yeah, 100 degrees. So in this case, we can still find this one is not equal to 0, but some values here are that's equal to, approximately equal to 1 plus 1 epsilon minus epsilon. And in this case, we take this approximation minus epsilon squared. So that is 1 over 1 plus minus 1 4. Okay, so that is, you can see here, this one, even energy is here. So that transmission is not 100%. It depends on lambda, or depend on, this lambda depend on how this V naught high. So that is not equal, it depends on case, right? So the curve is like this. T, if this is 1, we start from this 0 case, energy equal to 0, and then, this is here, right? 0 to 1, that is maximum, right? So then this curve is something like this, close to that. That is for energy use. And you can, this, some final values. So this gave us the probability for this tunneling effect. Textbook consider this if classical. For classical limit, that limit that this effect is ignorable, so that is go to 0. We will not. This is a quantum constant, right? The fact the or parameter. So that classical limit is that this effect ignored. Then you will see the lambda will go to infinite. So you can see lambda here, right? Then the t actually is go to 0, and that go to the classical limit. Since classical limit, there's no any transmission, right? All 100% reflect. Okay, this example is just consider we have just a square. It's like the barrel, right? But in general, it's kind of potential something like this. Text will discuss in detail how to deal with this one. Just make this divided this in each element, and each element as this the rectangle, this potential barrier, right? Then they discard like this and just integral with all the possible, but the effect is the same thing. So I think that's usually, yes.
This might be a really
Yeah.
dumb question. For where you did classical limit,
Yeah.
you say h bar goes to 0, but h bar is just a constant, so how do you...
Yeah, that does not mean h bar goes to 0, but just compare with the other, the quantity which we always use here, we have h bar here, right?
Yeah,
So this one, compared with this, is ignorable.
okay.
That is,
Okay.
yeah, that is, because if this is not ignorable, we still consider quantized effect, something like that. But if classical, that effect became very weak, so we can just say that is the language say that you just consider.
Does that hold in general that like if we have a quantum process and we make h bar go to 0, it becomes its classical form?
You mean the mathematically, right? Not this experiment, right? Experiment,
Right.
yeah. So for example, whenever we discuss, we have the formula from quantum mechanics result. Then you can just discuss the phenomena, because this is pure quantum, right? So then the pure quantum, you can just discuss if this one, we just consider this one is ignorable, or try to see that is, or this one is does not controlled by this importantly, or then you can close to that kind of classical limit. So that means this effect, if this effect is very small, then you can just make this mathematically assume this go to 0. But as he said, it's not 0, just the effect. If you remember, we have discussed at the beginning of the introduction, right? We say that is the matter wave, the de Broglie wavelength. and you also have one a homework, I remember. So in that wavelength, that is either classical or quantum mechanics, and you have depend on the wavelength. If the wavelength is certain wavelength, you have considered quantum the waveback behavior duality. If the wavelength is very short, you will see it's not just a particle behavior. The behavior is almost disappeared. So this one, this play the role. This one, this does not play the role. If you remember, go back to this homework. We discussed this classical limit, chapter 1. If you can go back to chapter 1. Discuss what is the classical limit associated with the H bar. Okay, so far you can see we discuss the energy spectrum. There's no limit, no restrict these correct numbers, right? All the energies keep continue, and only the phenomenon we are interested in is transmission or reflection. The particles still keep continue energy, but only when we have energy step or energy barrier or potential barrier, potential steps, what happens is just how keep continue or reflect. So that is this actually two cases, right? One is potential step, one is potential barrier. Now we consider another category that if the particle is limited in a certain range, that is called bounded state. This is unbounded, right? In that case, what kind of phenomena quantum mechanics? How about the energy? How about the wave function? So the remaining today, and I think almost only one case, we will go back to this potential. Go back to this case, the energy is connected. So the most case we consider others bounded states. What kind of quantum phenomena we are going to see is, let's consider infinite square ion potential. Let's consider this one first. Then we go to finite. If we know this infinite, so we know how to do the finite, right? Let's first consider this A is asymmetric. Then we go back to the symmetric square wave. Asymmetric means now here this potential as a function of x. Now we have, so suppose we have 0 and at A. So the potential, let me write down the formula here. That is infinite when x negative, and 0 when x between 0 and A, and then infinite again when x larger than A. So infinite means infinite, very, very high, right? So in this case, first we have the potential, then we are going to see how to solve the Schrödinger equation, right? Hamiltonian is kinetic energy, if we write down here, and then kinetic energy is this one, e squared x and plus, because, okay, so,
Why is this asymmetric? What makes this asymmetric?
sorry,
What makes this the asymmetric square well?
respect to x. You see, this, if symmetric means, if symmetric for respect to the 0, so the, let me give you a symmetric.
Minus A over 2.
Yeah, if symmetric, that means this potential wave is symmetric with this 0, right? But now, it is only from 0 to A, so if symmetric like this, if whatever plus minus, that is this one. I just want to, when I discuss, I will do this, but if you ask questions, I'm going to say this. This is symmetric, right? Yes. So, we are going to discuss this in details today. But then we have this Hamiltonian, like in here, and then Hamiltonian is also, if infinite, we will not interested, right? So that is only for this area. because others are infinite, right? Then that is the first potential. Then with this potential, how about this behavior of a function? Before we solve the solution, the equation, but at least we know if it's infinite, there's no way to find the particle above or outside, right? So this one must be 0, since outside is no particle can go. If finite, there's a possibility, but infinite, that is assume that there's no. So equal to 0 for x equal to 0 and 8. That is condition. That means we do not need to show the wave function in the whole space. So that means the equation or whatever time independent, time independent Schelling equation or the eigenvalue from either way, right? Schelling is only for this. So now we have h of square root 2m and d squared sine x dx squared equal to, right? And the interesting only for this localized between or inside the wheel. So we just solve this. Okay, and the solution. So this one is very easy, right? So let's give you a solution. Possible solution mathematically, let's first give up, is a prime exponential the positive kx plus another coefficient exponential minus prime kx. And here I introduce k. Let's define k is not the 2me or h1, right? That is. So that is general solution. Okay, now we are going to discuss general solution this. So now first, when x equal to 0 is equal to 0, right? It's satisfied boundary condition. I know you still follow the order, so okay, I wait. Sorry.
Good.
Yes. All right. So now the solution. Let's first the general, and then we are going to determine the coefficient, right? So now let's first use this one. If x equal to 0, size equal to 0, because we know it is infinite, so substitute into here, then we have a prime, because exponential x is 1, right? A prime plus b prime equal to 0, right? And immediately we have a prime is minus b prime. So the solutions be like this. A prime exponential I kx minus e minus I kx, and we know that is 2a prime sinus of kx, right? Then I'm going to combine 2a prime, they're just constant. So that is the function satisfy the condition, boundary condition, right? This is boundary condition. When we solve the solution, we need to test or use the boundary condition to determine coefficient, and sometimes also determine energy. So that boundary condition is very important. That's for a specific case. Each different case has a different type of wave function or eigenstates. So, okay, we have not get eigenstate. This is solution, right? We have not. Then this for this, and we have another boundary condition because x equal to a is also equal to 0, right? Then for the case of sine x equal to a, that's also equal to 0. Another boundary condition. The second boundary condition. We have two boundaries, right? Then we are going to see here. Okay, a sine ka equal to 0. That is false to have this. then that means, does not mean K is be arbitrary. Since A is constant, this coefficient constant, so ask this equal to 0 speed, this one is equal to 0, equal to n pi, right? So that gave us the condition here, Ka is equal to n pi, and now here, n, I'm going to, 0 is one case, but I'm going to discuss 0 with why it is not, so let me just give us, to not make mistake, so I want to start from here. So n equal to 0 case, we'll discuss later, right? Discuss. We'll make discussion, but keep in mind, mathematically, yes, n star 0 is fine, but basically, n equal to 0 is not acceptable. Why? Later we are going to. So now, what does this mean? So this means the K is not arbitrary number, not continuous. So we use index here, right? That is allowed value, right? Allowed value. Then why we have this correct? This is totally from the boundary condition. So that is means this is really come from this the particles localized in certain range, right? Okay, with this one we immediately got energy. Since our key is interesting is energy, right? Energy now, if A is K is quantized, if we say this allowed just these correct numbers, then energy K has energy relation here. So energy is h bar square n square pi square over 2ma square. And 1, 2. All right. So now by solving that time-intimate Jordan equation, we have the solved with the function or the states, which now we call the eigenstates and eigenvalue, or allowed energy and allowed. Now I'm going to here, since this k is quantized, right? So now the function we also use index here now. Is a sine n pi x over a. So that is solution, and of course we have to make a more, since the function is in principle in the whole space, so let me say if 0 with x negative, and non-zero only in the wheel, inside the wheel, n pi x over a, and 0 again. I write this way because the wave function in principle exists in the whole space. Okay, only this infinite potential wheel, so the wave function outside the wheel is 0. That is solution. Now we are going to discuss. So
third wave function.
yes,
The third wave function for x greater than a or x.
Yeah,
Which one?
x greater than a.
Third one.
part one. Sorry.
You have 0, x less than 0, and then 0, x greater than 0.
Oh, yeah.
It's greater than a.
Third one.
Ah, this is square, right?
No, in your wave function,
Big function.
at the second 0, your third line, it should be x greater than a. Down one more. X is greater than a.
Sorry. Yes. Okay. Yes.
Quick question, does
Yes.
this imply that the energy it takes to move these two potentials closer together is the energy that the thing inside it would gain? So like if we started off with an A with like a distance between the
Yes.
two greater than each other, and
Yeah.
we started to push them together, the energy we're doing to do that would be put into the thing in between.
Yes. I mean the energy. You mean if they change the A, right?
Well, yes, but
Increase E.
not yet. Decrease A, increase E.
Yes.
But is that implying that that is the energy it would take to move the potentials?
Not move the potential. This means the allowed particle within move inside the wheel. The potential is there.
Right. But imagine if we squish them, as we're squishing them together, the
Yes.
energy of the particle is getting higher. Right?
Yes. Yes. You mean
That
get
energy
rid
has
of
to-
the potential?
That energy has to come from somewhere. Does that mean that it's taking energy to push them together?
I didn't follow. You mean, you still discuss about if A chain, or just consider without, A still fixed?
Imagine if we had two scenarios.
Yes.
At time equals t equals 0, the distance is a. At time at a later t, the
Yes.
distance is a over 2.
Yes.
The energy has been increased, but energy should be conserved. Where did that energy come from? The action of moving the potentials?
You mean the energy is conserved? Let me think this way. When you move, you just you know that when you move, this is one of the example. So you have an external force to make this wall
Yes.
start the chain. So the system actually, I cannot say it's energy conserved or not. That I think.
Would what we've done be valid for that case? Because this is time independent, and if you
That's
were,
Yeah.
if you were moving it, it would be a time dependent situation, right?
Yeah, okay, that is also, if you want to move slowly, then you can consider the potential as a function of time. Then you probably need to consider the time differential equation. Yes, that is. But if you discuss, just consider, I ignore how the process of how the wall move from this way to this way. I just consider in this case and this case how these two energies are conserved or not. That I cannot say. Yeah. Okay, good. So now let's discuss some of the issue here, or the physics implied here give us the information. First, we discuss this energy, right? So energy here, it is quantized since it's not continuous, right? Or quantized or discrete. That is different from this the previous discussion, and the reason is because it's bounded state. Bounded state. Since the particle is bounded within the wheel, cannot go outside, cannot not allowed to outside the wheel. Because of that, so we have the quantized behavior. And then the second one, okay, quantized is due to that boundary, due to the localization of the possible particle motion within a certain range. Now let's first consider what is ground state. State means ground state, energy, and the function, right? So when we say ground means the minimum, right? E minimum. E minimum here, that we can mathematically discuss this case. So if n equal to 0, then what happens? We have the formula energy is equal to 0, right? How about this one? Corresponds to the wave function of this one. Here is also 0, right? So that means no such states. If 0 means the particle always has some probability to find a particle. If the wave function is 0, no probability to find a particle, so that does not describe the particle, right? So that means this is a not. Then we have go to the next one. N equal to 1 is smallest, right? From energy. And that's why we ignore this job, this n equal to 0 case. And I will come back to discuss this one in general at the end of this part, at the end of this discussion. So then n equal to 1, E1 is ground state, which is h bar square, pi square over 2, and a square. That is ground state energy. They correspond to states psi n equal to 1, and that is, let me keep A, we are going to determine A later, sine pi x over A. Oh, I will also to 0 when x less than 0, x between 0 and A, and 0 x less than A. Then next one, how to determine the excited states? Excited state, and that means is above ground states, right? So that's S here. But the excited states is definitely when A to first. The first excited state is the energy level above the ground state, so that is for the first. Excited state. Here, n equal to 2, right? So E2 is 4 h squared pi squared over 2 m squared. And sin 2x a over sine 2 pi x over a. And similarly, second excited state, n equals 3, and you follow the same thing. You can go higher, so depending on which question asks us, you can find the corresponding dot 3 pi x. So that is, okay, I always, in principle, add 0 to that, because that's more. This only for x. Okay, so do the others. This is how when we ask us find the first or second excited states, how to find the first one is the ground state, then above the ground states you will find the others. Is non-degenerate. Why? When we say degenerate means for given energy, how many correspond against states, right? So you can see here, for given n, we have only one. That's because this is 1 to 1 correspond each other. For one energy, we have one state, so there's no degenerate for this case. Number 5, let's look at the energy spectrum. So you can see here the energy. If you look at this one, right? This is the E. Suppose the E1, E2, E3, and E4 go higher, like this. So now, what is the energy difference between the adjacent or neighbor energy level? That is just difference between this energy level, right? Then we just substitute this into this formula here. Textbook also made some mistake, or they just remove this constant. That equal to this constant field here, 2m plus 1. Mathematically, we can do that. So textbook didn't use this one, maybe they just normalize this as 1. But of course, it's proportion to this term, right? Then let's look this. When n go to infinite, the energy difference with the ratio of the correspond to that energy level, what does it look like? In this case, we just substitute this difference, so that is h bar squared pi squared over 2m a squared and 2m plus 1. Denominator is h bar squared pi squared over 2m a squared n squared. So that is infinite 2m plus 1 divided by n squared, that equal to 0. And what that means, that is what I looks when I draw here. So when n go to high energy, you will see this one. Okay, first. This is not constant, right? Not constant means the space between each energy neighbor levels is not constant. It will change depending on n. Then this difference, this two energy level difference, divided by the energy correspond to that level, you will see it will, with n increase, it will go to 0. So the energy level is closer, closer, closer. The n go to infinity. those together. And indistinguishable. Is here, which that means in is that is like this. When they go to higher energy, you will see. So this type of the potential, infinite potential well, we can now we are I didn't plot well. Okay. So here this is a E1 and E2 and then go to infinite, right? Something like this.
Shouldn't that be like a logarithmic scale of some kind? Because the actual difference between them
It's increased.
is increasing.
Yeah. You're right. That is. But let me see this one. Okay. Yeah. That is. That is. If we characterize by this. That is closer, which correspond to, so that, yeah, that is high. In principle, you're right. It is according to n is bigger, just, but that bigger compared with this one is closer. That is that comparison here. Yeah. So here, okay. Let me just maybe not the absolute. This is E1, and the E2 is higher, so that is E2 here, right? E3 here. And this one is compared with E3, with this difference with E3 a little closer. It's smaller and smaller.
So this is, by saying it's indistinguishable, we're assuming whatever error we're doing is a multiplicative error?
Yeah, if distinguishable in case if. Yes, if the energy, when you have a higher, so difference higher is the n. Let's see how to explain this one. So this one is when we have higher, even though that is the difference is bigger, but compared with how high we are, that is this ratio. Is smaller and smaller. Just say this way. Okay, now let's go to 6. We discuss energy, then we go back to the wave function, the eigenstate. We have not get A, right, this coefficient. Now we are going to first normalize. That is, in any case, we are going to normalize our solution from the time-dimensional equation. Normalize is eigenstates we always want to normalize. That normalize means that's equal to 1, right? Then that is from infinite, because it's wave function state from negative infinite to the positive infinite. But we know the wave function only non-zero is in the range inside the wheel from 0 to A, the other 0. So this integral is only from A, non-zero from A, 0 to A, right? Then the remaining part is, so we just substitute this one into this formula. So we have A absolute square, and from 0 to A, sine square m pi x over dx. And the remaining part is just a simple math, right? That you can sine square alpha equal to the half of 1 minus cosine 2 alpha, right? So that is the detail to that. So you can do that one, the solution. This one gave a half A. That's b equal to 1, right? We are going to normalize. Okay, then we can have this normalized factor A is square root 2a. Then now, after normalize, we can back to this wave function we read, the exact normalized wave function. So here, okay. Number 7, let's double check whether they are orthogonal, because we know this eigenstates is be orthogonal, right? So now let's see. Also, check orthogonality, right? So here, anyone, the inner product if orthogonals be equal to 0, right? So now let's see here, that's equal to 0, minus infinite, plus infinite, so n complex conjugate, so m x dx, and again both the function non-zero from 0 to a, so that is only considered the integral within this range. Then here, that is the function, so we have 2, so that is 2 over a, right? From 0 to a, and then the sine, since sine is a real function, so it's a complex conjugate is itself. M pi x over a sine m pi x over a dx. Okay, this is also simple integral I just gave you. Oh, maybe Wednesday, I'm not sure you remember that, so let's just give you this product of sine alpha sine beta equal to half of a cosine alpha minus beta alpha, right? So that is n minus m pi x over a minus cosine n plus m pi x over a dx. So you can do, right? You can go to the cosine. So finally is this 2 to cancel, so 1 over a, and inside a over m minus m pi pi. And sine m minus m pi x over a minus a over m plus m pi sine m plus m pi x over a x minus a, and you will see x equal to 0 because sine when the x equal to a is this is the integer number, right? Always 0. So of course this is n not equal to m case. For n equal to m, we already normalized here, right? N equal to m. So finally combined together, you will see here the normalized orthonormal. Together, this discuss the 6 and 7. You can write this one, right? Okay. 8, number of nodes. Remember we discussed that there is a theorem that the number of nodes equal to n equal if the ground state starts from n equal to 0, or n minus 1 if the ground state is n equal to 1. So in our case, ground state is n equal to 1, not from 0, right? So the number of nodes equal to n minus 1. Let's double check. For E1 equal to E1 case. That means for n equal to 1 case, this is n, right? That is just if you remind you that we have a theory. So now, if you look, just consider the field case. Ground state is n equal to 1, right? So that is this one. That's that one. Yes. So number of nodes. Right? No nodes here. 0 here, A here, 0, right? No nodes between 0 and A. Then the second one is psi 2. Psi 2, you will see that is this function. That is m minus 1 equal to 2 minus 1 equal to 1. So we have, yes, we have one node here. Now, let's do another one. Say as the process, here you will see here, this corresponds to 8 quarter. This corresponds to the 3 quarter. And the psi 3 is for this case, m minus 1 equal to 3 minus 1 equal to 2. Yes, we have two nodes here. And you do it later for the highest. You can find that it is follow the theorem here. If we discussed before, the number of nodes equal to n minus 1 if the ground state is from n to 1. And later when we discuss the harmonic oscillator, you will see that n from 0, since the ground state is n equal to 0. Then the nodes is equal to n. Okay, so number 8, that is give how to discuss now. Number 9, how about parity? Do we have the parity here? As I already discussed before, right? Because the potential has no parity. So Hamiltonian definitely also has no parity. There's no relation between x and minus x. Then the Hamiltonian does not commute with the parity operator. Remember this parity operator? No. So if not, if yes, we know that they may have a common or joint eigenstates, and the joint eigenstates must have a well-defined either odd or even, because it must be a function of this parity operator. But here, no. So we have the conclusion that any will not equal to plus minus of minus. Not this part. So no will define. Later we want to see the symmetric and define parity. Okay, there is a parity issue we also discussed now. And how about general function? So any particle, if we have initial states and move inside of this well, what is wave function? The wave function to describe this general case, right? In general. That is because initial states may not one of the eigenstates. So, or this particle, a linear combination of eigenstates, right? So that's in general, project to the x or position representation, that is just wave function, right? Remember chapter 2, it says in the position representation, the cat is function, and that should be linear combination of n from 1, right? Allow quantum number from 1 to infinite, no any upper limit, right? And linear combination, you remember Cn coefficient, right? And linear combination of the eigenstates, so now it's like n, x, and exponential. This is a time dependent function part, I, E, n, or h bar t, right? That is any wave function at any time. Since this is a stationary state, so linear combination of these all the eigenstates. And how to find the coefficient? How to find the coefficient? Remember, depend on initial, right? That is how the initial states project to one of the eigenstates, right? So once we know this, that gives us initial states, particle in which state. So first job is we are going to calculate this coefficient. And this one is immediate. Let me just from the in general, right? So that is, and then we know this is only non-zero from 0 to a. So what you need to do is just this. And the function is square root of 2 over a. Right, sign the function, multiply. What the initial gave us, so we're going to type this. All right, so that's a mistake in equation. Here also textbook 483. They miss this one. Miss. So I just give you this. In case ask you to find this probability, you need this one, right? So that is okay. Now, let's go back to, I erase. We are going to discuss 11 is the 0 point energy. Remember here we have En and E ground. In this case from E1, right? Why not in N equal to 0? So we are going to explain the physical. What is the physical implication? What does it mean? Y have to equal to 1, not equal to 0. So now let's consider this case. Because x is limited, right? No, cannot go forever. So that means if in this case, we just start from this case and go to general. So because this one, so that means the fluctuation or uncertainty for x is A, right? Maximum, the uncertainty is A, and maybe the smaller than A, but it's from 0 to 8. So that is then from the uncertainty principle, we have either Heisenberg uncertainty principle or general uncertainty principle discussed in chapter 2, right? And uncertainty principle. Delta x, delta p, right? Now it's p is px, right? So we just dropped x. So we always larger than equal to. Who remember this formula?
H bar over 2.
Okay, that is conclusive. I want a general formula.
The 1/2.
Average, yes, average commutator, right? No, just average commutator. Yeah, there's a half, yes. There's a half, yes. And then the commutator is IH bar, right? Then that equal to, yes, in this case, yes. I just want to remind if I have two other different operators, how do you do? Let's try to remind me, learn before, right? So, okay, what that means, the fluctuation or uncertainty of the momentum, linear momentum. This must be non-zero, must not infinite, right? So that is given or equal larger than this. Now is 0. If 0 is not, does not mean so that means that is concluded, right? Because it must be larger than this, but this is a larger than 0 value. So that means the fluctuation or uncertainty for this linear momentum speed should not be 0. Okay, that is conclusion here. Then let's consider if we set n equal to 0 as a ground state, then energy is 0, right? So in this case, because energy equal to the kinetic energy plus potential energy, right? Potential energy, just say. Kinetic energy at zeroth case, how much we do not know, but equal to this. And since the potential in the potential well is 0, so that's equal to the kinetic energy. If, right? And the kinetic energy in this case be P naught square over 2m. And then this means P naught is 0. That contradict this result, right? This requires this fluctuation to be not 0. That means this one means to be larger than 0, right? So if we get 0, that is not acceptable because of the uncertainty principle. If that go to 0 means delta x go to infinite, and that is not true, since this is localized. Right? No. States. So for any, so that's why the ground states, the smallest states, the energy ground in this case, we go to the lowest one is V1. That is physical interpretation, and mathematically we already discussed when n equal to 0, there's no states, right? Psi 0 is 0. So from this example, we can extend to the general. For any bounded state or localized in general, for any bounded state or localized, right? For this case, because x always somewhat finite, right? Then require this momentum also finite response. Then that means the energy minimum or ground state, that's the ground energy, equal to T minimum plus V minimum. Classically, it is possible the stable states 0 kinetic energy. Just go to the minimum potential. That is the potential value, right? Something classically come here. We stay here. But quantum mechanics, if the state is localized, due to this uncertainty principle, it requires us, even in this case 0 case, but cannot be 0. Since here, right? Since the T minimum cannot be 0. That is means even for the, in quantum mechanics, even for the 0th point energy that is ground state, we have to require that the particle has a certain kinetic energy or linear momentum such that to satisfy this one is finite. Example like atom, right? So we know have in the hydrogen atom we have electron move around this the nucleus, right? And we always keep this ground state R0, which is not 0, so that we have a finite this one. This is localized such that we keep this stable. If we do not require this one, the electron will collect to the nucleus. Right? That is unstable. Right? So that is this response to this physical implication that to make the localized states stable, we always require certain, due to this certain of these localizations, the linear momentums we also require non-zero. You have a question?
I was just thinking about
Think
what
of-
would
yeah.
happen in a black hole, and I wasn't going to ask
Oh,
about it because
okay.
I realized that would be a terrible thing to ask. But you saw the level of thinking that was
Yeah,
going
so
on.
this is let me say, not the special case, right? Just
Yeah.
general. Now, black hole, we have add some additional condition there. So that is okay. I think I have time. Good. So now let's go to some of our practice. Just play when we deal with this type of a question, how to do that. Do some exercises. Okay. It's I think it's the first one. Let's ask us calculate this and prove this follow the uncertainty principle. Okay, so how to do this? First, we need this means A means correspond to states. That means given states, we are going to find this the uncertainty of the position and uncertainty momentum and see whether it follows the uncertainty principle. So now we need first to calculate this, right? If I use the operator here. So when I use n, that means do the average expectation value of this operator in the states of psi n, right? So we need first do this, and then we are going to substitute to check whether it is from this. So in order to do this, let's first calculate this one, expectation value. Then we are going to do this square, right? So expectation value in principle chapter 2 is this one, but we already normalized, right? So that is only equal to the numerator part. The position operator sandwich between this given eigenvalue. Since here, just sometimes if not normalized, do not forget this denominator, right? Okay, so this one, I think the remaining part is math. Now let me get the formulas. I just immediately give you the final result, since this is simple from 0 to 8. Okay, I still want to use, because sometimes later if we make that some other different case, be careful. It speeds from negative infinity to the plus. And first, x, since x operator in x position is x, right? And because the wave function, the eigenstates is only non-zero from 0 to 8, so we just now we move to 0 to 8. And here, the square root of 2 sine n pi x over a x square root 2 over a sine n pi x over x. Here, be careful, we have x here. So that's when we do the normalization, we have this sine square, right? So we can do that 1 minus cosine 2, double the angles. But here we have this one, so you just change this one and then multiply this into the two terms and do the integral of each individual. So let's get the result. The result is this one, and I just skip this intermediate step. Then here, let's do the P linear momentum, the expectation value of linear momentum first, and then we go to the square. So this case again, just be sine n x, P sine n x, and the linear momentum in the position representation is minus I h bar d dx. So here, still from 0 to a, I just skip this integral from minus infinity to positive infinity. Now here, and then, let me just write here, 2 a sine n pi x over a minus I h bar d dx. Here, be careful. This do the derivative is to the after this one, all these functions being moved to the derivative, right? So you do that, and then give you a result. The result is 0. When you do this one, you get the cosine, right? Sine cosine, and or you can another way which is just dx. Cancels out that is a sine d sine, right? So, and then this function, when you do this integral, you will find this is a substitute from 0 to a dot 0. This one is x squared, expectation value of x squared. I think this one is still also from 0 to a immediate, right? So that is 4 over a sine n pi x over a x squared over a sine n pi x over x. And the result, this one is complicated. We have non-zero term. Finally, a squared over 3 minus a squared over 2 n squared here 0 to a. This one is minus I h bar square, and this is a second order derivative, since it's p squared, right? Sorry, this is cosine square. Finally, this is non-zero, and the square is non-zero, but the p momentum 0, so that is n squared h bar squared pi squared over n squared.
We're supposed to have an extra sign there, right?
There. Oh, yes, you're right. Okay. This. So here, sine n pi x over a. So here. Yes. N squared h bar squared pi squared over b squared. Now we can calculate this delta x and delta p n. And you just substitute into those, and finally, okay. Since we are going to discuss only the relative integration, so that is a over 1 over 12 minus 1 over 2 n squared pi squared. N pi h bar 12 is 2 n squared pi squared. It is larger than, you can check yourself if you substitute numbers here. So we can find that is larger. It is satisfied. Second question, so now this is the second one, is acts of the I think that question is a 0 point energy. Energy. 0 point energy, because here now we look this, the lowest, right, delta P1 is high H bar over A. Then this energy minimum or the ground energy, since we have potential energy 0, right? So that is P minimum, which is delta P1 or P1 square or N. And that is nothing but this 2 A square plus 4 pi square. Yes, we double check. That is number 3. I think we cannot finish, but this question is like, so if initially the particle is psi initial, okay, let's say initial states x is equal to ground states of this energy states. And if the wheel is suddenly, right, so that is from A to move A, the wheel is extended suddenly to A prime equal to 4 times A. So we do not consider the intermediate, what happened from A to A. That procedure is very quickly, just imagine. Then, okay, then find the probability P, okay, at the new state, if I'm going to use set prime, and okay, that's set prime, and so here, that is probability. That means when we suddenly extended the wheel, we have to solve the Schrodinger equation again to find the eigenstate for that with the potential wheel. Then we have that eigenstates. Then we are going to find initial is one of the ground states of the narrow wheel. Now this is became initial states, not eigenstate of the final one. So then, what is the probability to find the particles in the ground states of the new wheel and first excited wheel? Think about this, and we'll continue to discuss this on Wednesday. Reminder, Wednesday we have due. I think you can do the homework, right? We'll discuss. Oh, you asked me the question about this sign 1 and 0. I think that is correct. Just follow my notes. Yeah. But if you did it, I can follow you or what you assume that function. All right.
And my computer's down in the GCA office, but do you mind to look at that and
Yeah, no,
point me in a direction?
I don't mind. Let's get that in here.
I mean, I imagine won't take but a minute or two of your time.
No, especially if it's similar to what I have.
Yeah, it's, I mean, it's.
Who called this particular?
Doctor, do you
Yes.
know when we might be able to expect the qualifier results?
You need to ask Dr. Jane Duquesne. She is the hold, and she's responsible for that, right?
Okay.
Yeah, I just one of the breeder.
That's okay. I know we're all eager.
I don't know, I don't need my-
Yes, me too.
I don't need my
That
hopes
is, that
crushed
is
yet.
one of the faculty has not yet finished grading. So she has to wait.
ID number 1.
But,
Very
yeah.
Who is your investigator? Okay, then I can email. That one's on the way back to me. Huh?
Check this one after the video I review.
Reading through, like, is there any surprises or anything like that, or is it just as simple as it looks?
It's so simple. That's, yeah.
I started to do the thing where we reached like the halfway point of the semester or whatever, and I had previously been helping out. I had previously been helping out the students like set up like their data and stuff like that. And I'm like, we reached the halfway point. You all should do it yourselves.
Wait.
So I had to do the whole speech where I was like, from now on, you all are gonna have to set up and take only your own data, and I'm not gonna help you, blah blah blah. Which basically just means I've gotten tired of doing the labs myself, so you know.
The only thing that I could think of, well, in the video, he writes on the whiteboard, but we don't need to show that. That's just if
Yeah.
you really want to. If both photo gates should be corresponding to the same timer.
Yeah.
So if let's say cart 1 goes through the photo gate and it gets a time, and it pushes the other cart through the other photo gate, and it's supposed to add on to that time. In the case this morning, we had to reset both photo gates so that they would contribute to both the time, because only one photo gate was collecting time.
All right, make sure both of you.
Yeah. So that, that's the only real thing.
Cool. Thank you.
Thank you. Yeah.